So we have been graphing quite complicated higher degree polynomials, and this is going to be our second method that is much easier to understand if you understand the previous method. So I'm going to use a lot of the things that I explained in the previous 3 videos about these polynomials. This is a shortcut. Let me first show you this technique and then I'll explain why it works. Okay. First, let us assume that we factored out all the leading coefficients from the linear factors, so it is brought in the form that it is most suitable for graphing. Okay. First, we're going to figure out the end behavior. For the end behavior, for a second, let us forget the exponential notation. Okay, so we do not have to write it out like that, but it is good if we can think of this polynomial as really this product. All the zeros happen at a finite fixed number. Now imagine that x is a gigantic negative number. It's so very much negative that every single linear factor here is in the negative, right? Line with a positive slope starts out in the negative, takes a 0, and then it's positive. So at the left edge of the graph, every single linear factor is negative, so the question is how many negative signs do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 negative numbers, when we multiply them, that's negative. Imagine that this is the screen of a graphing calculator, and so at the left end of the picture, the graph is coming into the depicted part of it from way below. We're going to do the same thing on the other side. Now we're going to think of x as a gigantic positive number, large enough so that every single linear factor here is positive. Then we have exactly 1 negative sign. All these other factors are positive. So this is the end behavior. Okay. So after we establish that, we're just going to go straight to graph this thing. There's not going to be a table or anything. So we're going to start with the zeros. There is a 0 at -4, at 0, at 2, and at 5. And we already know sort of this much, that the graph comes into the picture way below and leaves the picture way below. Instead of thinking in terms of positive, negative, we figure out positive and negative at the end behaviors, and from then on, we don't care about positive, negative. We only care about will there be a change in sign or not. Okay. We're going to head into the first 0 at -4. And then, if you have been graphing these polynomials, you know that there are 2 things that could happen. The function values will change sign from negative to positive, sort of like a line or a cubic function, or it might bounce back and the function values remain negative, like an upside-down parabola would do locally. And which one is going to happen will depend on the exponent of the linear factor that is 0 here. So at -4, the 0 is caused by x plus 4. Its exponent is 1. 1 is an odd number, so we're going to go through. Surprise, surprise, we're going to count negative signs again. So we go through, then we turn around and head towards the next 0 at x equals 0. And again, we have 2 options, go through and change sign, this time from positive to negative, or bounce back and remain in the positive. We look at the exponent of the linear factor that causes this 0. The linear factor is x, and x is squared. That's an even exponent, which means we are not going to change sign, and we're going to bounce back into the positive. And then we turn around and head for the next 0 at x equals 2. At x equals 2, the function has a 0 because of the linear factor x minus 2. That is at an odd exponent. Therefore, we're going to change sign from positive to negative. I'm going to try to make it a little bit more cubic looking. And then we turn around and head into the 0 at 5, but you see the end behavior is already suggesting what should happen. And indeed, the 0 at 5 is caused by the factor x minus 5, and that factor is raised to the second power. That is even, therefore we're not going to change sign. It's pretty nifty. It's much less work. Why does this method work? Suppose we graph the same function using our previous method which is figuring out the behavior of the factors and organize them in a table, and then using that we decide how many negative numbers are multiplied at a given interval. So really quickly, x plus 4 has a 0 at -4, at x equals -4. It's negative before, positive after. X squared, on the other hand, has the 0 at x equals 0, but it is positive before it's 0 and positive after it's 0. So that whenever the exponent is odd, we're going to have this behavior of changing sign from negative to positive. Whenever the exponent is even, we're going to have this boring row of just plus, plus, plus. This minus, minus, minus is caused by the leading coefficient. Okay, so now why would this thing work? Why would an even exponent cause no change in sign of bouncing back behavior? Let us consider at x equals 0. This would be the algebraic look at what happens from one side of 0 to the other side. This is before 0, this is after 0, before 0, after 0. So what you notice is that the two columns are completely identical. There is no change occurring. Now why is that? Well, there is no change in the first factor because x plus 4 has the only interesting moment in its life elsewhere at -4, right? Nothing interesting is going to go on with the factor x plus 4 around x equals 0. And that is true for any other factor. X minus 2 cubed has its only exciting moment around x equals 2. So whatever happens at x equals 0, there is not going to be a change in sign in that factor. That just happens once at x equals 2, and so on. So at x equals 0, from one side to the other, no other factors will change sign. The only thing that can change sign around 0 is a linear factor like x. That's the only one that has a chance to change sign, but it doesn't because it's on an even exponent. We can observe the same behavior around x equals 5, right? If you look at these two columns, they're completely identical sign-wise. On the other hand, if the exponent is odd, like in our case, let us look at x minus 2 cubed. From one side of 2 to the other side of 2, we're going to observe that, first of all, the other factors will not do anything. If they were negative, they remain negative. If they were positive, they remain positive, because their only one interesting moment of changing sign happens elsewhere. The only factor that has a chance of changing sign is the one that's 0 at 2, and that's x minus 2. And x minus 2, because it's raised on the third power, does change sign from one side of 2 to the other. Therefore, the entire function will change sign from one side of x equals 2 to the other side. So this is why this works. Let's see another example real quickly. So we're going to grab this function with our slick new method. So let's start with the end behavior first. This is two linear factors, x plus 3, x plus 3. This is 3 of them. This is 2 of them, 4 of them, 1 of them. So all together we have 2 plus 3 is 5, plus 2 is 7, plus 3 is 10, plus 1, 11. So we have 11 linear factors. So imagine that x is so large negative that all these linear factors are negative. Then we have 11 negative factors, and this one here is the 12th one. So what that means is that if we multiply 12 negative numbers, the product is positive. So on the left edge of the graph, the function comes in from way above. What about the other side? The other side is kind of easy, right? Because there is just one negative sign, and that's in -2. So that means that we leave the picture like this. Okay, so now that we established the end behavior, we're gonna draw the zeros. It's not very scaled, sorry. Okay. Oops, I didn't leave myself much space. So we're coming into the graph from way above. The first 0 is at -3. The 0 at -3 is caused by x plus 3. That factor has a multiplicity of 2. So in other words, it's on an exponent of 2. That is an even number, so we bounce back. We do not change sign from one side of -3 to the other. And then we're going to head into the next 0, which is -1. That 0 will carry a change in sign because the linear factor causing the 0 has a multiplicity of 3. And then we turn around and we're going to head into the next 0 at x equals 2. Because the exponent there is even, there will be no change in sign from one side of 2 to the other. The next 0 is at 4 with a multiplicity of 3. That implies change in sign. And finally, the last 0 is at 5, and its exponent is 1, which is odd. And so we change sign, as we find out, from positive to negative, which indeed corresponds to our prediction based on the end behavior. So there it is. It's pretty nifty. Thank you for watching.